What we're going to do now for a start is talk about linker script. Now, usually when people teach linker script, they're going to talk about how we take some file, okay, some object file that has been compiled or assembled, or actually both, and use some magical tool called the linker in order to go and actually make like the final image. Now, a lot of time we hear about linkers when in the context of dynamic libraries, it is shared object files or static libraries. And while they are very, very, very important, linkers actually have also more basic approaches, which all of you do embedded development and ever had to write some bootloader or some bring up code know what they are. That is simply specifying what is going to lie where in the memory. And I'm just making sure, can you guys hear me? Can somebody jump on the mic and say that you hear me well and you see the screen so that I will not be interrupted?
Yes, will.
It's fine.
Good, good, perfect. All right. So what we're going to do now is to take care of like, see how we actually construct an elf, see more or less what is an elf. I will assume knowledge of that. If somebody misses knowledge of that, then please let me know and I'll explain a little bit more. Okay, otherwise it would just take a lot of time. But during the examples, I will always like give the rationale. So please do jump in with questions. This time, as I promised, I'm going to make things shorter, but I'm going to be very, very, very flexible according to what you guys want. So no questions, no comment. I do whatever I want, and you know. All right. So what we're going to do is this. So here goes. So we're going to start by looking at. Never mind. This is something that I adjusted because I put like a note for myself. Usually, when we talk about ELF or PE in security orientation, is that if you get something, some binary, you want to see how it's made, and a lot of times teaching those containers is very important. But now we want to do the other thing. We want to understand what we have in hand, how they are built, and then combine forces with sort of reverse engineering what we get when a kernel is built, and all the extraction script to make sense of them, like where they are, how they are, and understand at the end what is the compression and uncompression phases in the Linux kernel boot, in its self-relocating phases, and so on and so forth. So relocating have several meanings, and in the context of this talk and probably tomorrow, I talk about very, very partial relocation, that is copying some piece of data from one place to another in memory. Okay? So I will not talk about it too much. We're going to concentrate on the 32-bit Intel architecture that I did earlier. Everything that I say now applies to all the platforms. About the linkers, for sure. When I'll talk about the kernel, then most of the things in the 32-bit are also applicable to the 64-bit, all right? And for ARM, many things are applicable, many things are not. When we talk about how the kernel boots again, then we will, all right? So the first thing that I want to tell you is what linker scripts are, all right? So just so you know, and let's go and I think it was step 1. I didn't do it in Git on purpose, just so you know. Let's say that I have the following thing, okay? Temp that I'm writing right now. If I have a file, okay, let's say echo main, because C likes it, into whatever.c, okay? And I do gcc to whatever.c, then the default file name would be a.out, right? Now I could give it all kind of other parameters on the way, all right? And I could also not like build it directly. I can just like maybe just compile it, and then I will have something on the way that is like the WTV.O, right? So I can also just see like what the preprocessor says. I can just, for example, just assemble it or like get the assembly output of it. Okay, that is this guy in this case. All right, it doesn't do too much. Like this is x86-64 in this particular case. We have here main that is going to be an exported function. Okay, it has all kind of things, and we have like a preamble that doesn't do anything, and return from it. Where to return to libc, for example. Okay, so what we did here, like GCC actually, when I just do GCC without anything, then it does several things, right? I mean, it assembles, it compiles, okay? This is intermediate code, so I can actually just go ahead and use this exactly as if it was like the C file. It compiles it into like the object file, and then it links the object file into like the final result. So the guy that is doing it is called the linker, right? So it's LD, the GNU linker. We also have LLVM LD, which is Clang. Or Clang is a part of LLVM toolchain, so it's their linker. There are several linkers for GNU also. There is Gold, there is LD, there is this, there is that. And what the linker does, essentially, in this particular example, is this. I'm going to use ObjDump a lot because it's like my disassembler, and readelf. Okay, so if I go ahead and look readelf at wtv.o, I will see all kind of things that we will explain. I will do it with a w because this should be -w, I guess, or white one. Okay. In ObjDump, it's a lowercase w. Okay. So I just wanted to see this, like all the lines. So readelf does several things. It gives me a lot of information, okay? And now I'm doing it on the object file that have a header. The header have all kind of like pointers to some tables. I'm being very like informal deliberately. These tables tell all kind of things. For example, section headers table tell me where is like the text segment or section that has been defined in the file that I have in this .o, what is its offset like in the file, where it starts, and so on and so forth. And what it also tells me, if I have some symbol tables, then it has all kind of indexes over there. Okay? So essentially, readelf tell me information. And some information is very important, some information is very not important. If the file is like an object file, we will see some things. For example, that its entry point address is 0, okay? And if the file is a fully linked one, like this A out that we had, then we'll see all kind of other things. So here we see CR stuff, we see like all kind of strings, okay? We see Gmon start, we see libc start somewhere, we're supposed to see it, okay? Libc start main, okay? It doesn't come from our empty main, all right? And we have here dynamic symbols, and we have here relative, and we have here all kind of things. For example, it needs libc, and we have interp somewhere that interp tells us, hey, this is the interpreter. This is what we'll read. For example, if you have like load folders and so on and so forth. So we have these things, okay, that were automatically generated for us when GCC, the command, took this object file and linked it into a.out. Now, what happens? Now we need to explain a lot about ELF in order to, be very Catholic or like very Orthodox or very whatever you like. And we need to explain it, and I will not really do it unless there are questions. But what happens is something very, very interesting. When I use GCC, and I'm not going to tell you how to debug GCC, there are a lot of like hidden switches. Some of them, GCC, which is the GNU compiler collection, it's a collection, okay? Some of them, they are going to be configured into the tool. For example, right now, if I look at a.out, then it's a shared object, okay? And it's positioned independent code, probably. Why? Because this is how GCC was configured to do it, okay? I mean, it's LSB shared object. I mean, what? I know it's an executable, so why it is? If you look at it in older version of Ubuntu, for example, or of the GCC configure for there, then you'll see that it's like an executable perhaps, and so on and so forth. Okay? So what happened here? So some of the things that we have, like on LD, if you use the -- verbose, then some of the things that were happening were actually made into our friend here, GCC, that invokes LD as part of the thing that it does. So let's see what we have here. So ld.verbose, tell me some information. I didn't run it on anything, but if I ran it on the file, it will tell me the same thing. It says this is the version. These are the emulations that are supported. And using an internal linker script. And here we have a language. Now I will not go over all of it, but I will emphasize some of them. Output format, that is what is the container in the architecture. Output architecture, this is very, very important, okay? Output format is super important. Like you don't even have to have an ELF. There are also other formats, okay? Entry is the entry point. That is, if you have such a symbol somewhere that you link, this will be the entry point to the target. When you see entry in an assembly file, then a lot of times it's like a macro that says, hey, this is the start of a function. This label is like a start of a function. At least super common like in the kernel, okay? Search dir, like where to search for all kinds of libraries. And you see the highlighted libraries, you can see that like, okay, it makes sense. This is where I expect to have libraries. And then we have this thing. Now, a lot of people, like, you know, they come from JavaScript or they come from web programming and they love JSONs, okay? Or some people come from a device tree blob programming and they love DTSs. So they have this notation that make things like very organized, JSONs, XMLs, the DTBs, and so on and so forth. And this also has its own language. Now, we have here sections that is going to be quite long, and I hope you see well enough because I'm not displaying everything, but some of the things that we saw when we did readelf, we also see here. So we have the interpreter, and we have the reladine, and we have an init section, and we have the PLT, and the GOT, the global offset tables, and we have for structors, and we have provide that essentially says, hey, if nobody provides this symbol, like if no object file had the symbol eText, then no problem, I will provide it. And it has dot that says, hey, this is the current location, the current address. I will repeat it again with slide, okay? And it has all these kind of things under section. So there is a language here, okay? So still under section, I will skip to the end. It has alignment construct, like say, hey, this address starts exactly here, okay? It has all kind of things that look like symbol tabs and like debugging and so on and so forth. And it also says, all right, if I got from another object file that I was linking these sections, I don't care about them. Throw them away, okay? So if I don't do anything, I get a lot of information by LD. But what if I don't want all this, okay? So what if I want to do things in a different way? So we know we can affect GCC like in all the other tools by all kinds of switches. So we can do it. And for many things, you can affect things completely. But now what we will want to do is to do something else, to say, okay, we don't care about this at all. We don't care about the defaults. We want to use our own linker script. This is our constitutional right, okay? To do whatever we want, to have no external dependencies. So that's what we're going to do now, all right? So that's the motivation. Any questions so far? Yes, I will briefly tell what's else, but listen up. Like, it's very, if there is a question, I hope I answered a little bit. If there is a question, I would want you guys to just go over the microphone, because otherwise there is very, very, very good chance that I will not see it until I finish. All right? Okay. So speaking of elf, like this is an example of elf. All right? An elf is essentially a container. And when I look at the binary file, like this nice whatever that O that I made, it has a description. I just made the main function that didn't do too much. But if I look at it, let's say with an Hex Dump, okay? And I did something wrong here. Yeah. If I look at it, then I see thing. This is how the file really looks on disk, okay? So I did it with -C so that we can see on the right-hand side strings, okay? And we see that the string will start with .elf. That is dot, when I do Hex Dump, it means a character that is not printable, in this case, hex 7f. And these are the hexas for ASCII of ELF. Here I see all kind of string like GCC Ubuntu. Here I see all kind of strings like the section names that I had, okay? And there I either see or not see all kind of things. I said all kind of things many times. Now, there is actually logic in whatever is happening here. Now, one of the things that I will have, assuming I have code, is essentially, and now I will use my nice friend here, Opcode, to disassemble this file. One of the things that I will see is code, and the code will be like in bytes, right? Like there are bits that are actually making sense of like the information. There is a machine code. There are mnemonics that are these guys, but they are translated to, okay, 55 is push, CC is breakpoint, stuff like that in Intel. Okay, those who don't speak Intel, sorry. And the idea here is that no matter like what I do, when I run a file, the information needs to be somewhere. So I could theoretically, potentially have a file, if I just want to do these commands, that will have only these ones and no structure. So I cannot put like debugging symbols. I cannot, if I want to load or use external libraries, I cannot specify them. I cannot tell where I load myself into memory. So if this is loaded at 0, then I need to somehow externally decide what I do with this. I could have this, and this is called like a flat binary like without a format. But if I want to do things that are more complex than what I would want to have, and I'll get you back again like to read elf, and I'll do another lecture about elves, okay? And this was with the -w to be short. What I want to do is like, this is on the same object. I want to make sense of what it is. So I'm going to have all kind of like tables, okay? Like say, hey, if something is in the text section and it's like executable, for example, and it's allocatable, that is, hey, put it like in the memory, then I want to take the code over there and put it like in executable pages, all right? So these are going to be in something called program headers, and we'll talk about these things later as we like construct it. Okay, so an elf, like in a graphical way, looks like this. It always have a header. Yeah, is there a question? It always have a header, and it has pointers to the different tables that it has. All right, a very good example for it would be to actually open the include files for elf in your user space, user include, and so on. Okay, so we have all kind of tables, and some of the things like section header tables it will point, each section will point to a place that is like on like the text section, or if you have data, it will point here. If you have BSS, it will point here, and so on. So it's like tables of offset that makes a structured way. Okay. Now, just so that you know, like before we did hex dump, so let's do it again. Okay. So we see here like, hey, sim tab, str tab, SSH, and so on and so forth. Things that are human readable are easier to understand. And we see, for example, that like we have here 1A0, 1B0, 1C0. Just so you know, like when we have these guys here, there are section headers. Like for the section headers string table, that is the names that we see like of the section itself, they're going to be like in the file in the offset 1A8 they start. So if I look like here at 1A8, then I actually see the strings and so on and so forth. Same goes for debugging information, same goes for everything. There is structure for everything, okay? Like if you have a debugging information under the sim tab, it's not debugging information, it's like symbol table, it's not the same thing. Debugging information, there are several levels of it. Then we're going to see the whatever.c in the corresponding like place, and so on and so forth. So ELF is essentially a structure. Now, who does something with a structure? It depends, okay? Basically, I could have some sort of another program that loads me, that knows to interpret it. And when we look at the Linux kernel, we see, for example, what it does with the ELF, okay? I'm saving some time here because things can be complex. All right. Any questions or any so I will talk about the motivation to create our. I'm not talking about creating our own loader. I'm talking about creating our own linker script. Okay. The motivation is to control what you want to do, and like a trivial motivation for that in embedded would be like, hey, you get a board and you want to start executing things from address 12340 on the memory. Okay, what is executed there? What is loaded there? Why is it loaded there? What is the mapping? What is ROM? What is RAM? Okay, so this is like for the embedded case, and like for the Linux case, what I said before, the motivation is to explain like how the kernel is structured, actually for all architectures. And if you understand linker script, you can say, hey, why do I need this run for? I'll just see it myself, okay? At least for some of it. All right? Itai, does it answer your question? Yeah, no worries. Next time arrive on time. No, I'm joking. So we're good. And besides you did, I think. So, all right. So guys, please jump in on microphone like to take my attention. So here goes. What do we need? What is LD? Why do we care about it? So already saw what the LD -- verbose. So in order to produce a binary, what we need are object files, okay? In the right architecture and to put them together. Basically, and there's a trick I can use in order to have like a linker script of my own. As long as the file is not like empty, then I can work the linker on it. If the file is completely empty, then it may avoid, okay? Now, a linker script would be something that, like what we saw in LD -- verbose, that we can provide ourselves, and we can either provide it as a standalone, like in this case, it's our entire linker script, that's it, or we can actually go ahead and add it to some other things. So the minimum requirements in order to actually use LD, for example, is not to have an empty file. And this is when I put something and emphasize, unless I like forgot to, okay? And it means it's a shell command. An empty file, LD will say, hey, file not recognized. But if I have like even just a comment, this is how I put comments in LD, not a @, not // not this, not pound. If I just put a comment, then it will just say, all right, let's work. So if I have a file that only has a comment and I try to link it, then it's going to say, hey, What's that? I can't find the symbol underscore start. And who expects underscore start? Apparently LD. Now, you don't necessarily need to have a symbol, but you need to have an entry point in it, like we saw before. So if I just came and try like to see what A out, I will see that it's actually something that works. So I can go ahead and see what is the result on it. So let's do this. Non-empty file, okay? And I'm going to do LD on X. And I'm going to see what A out is, all right? And let's do X dump on A out. Let's see what it gave us. So it gave us a shorter file. When you have hex dump and you see this, it means that the other lines until this are identical. So from F0 to 130, X, everything is X, and that's what we have. The nice thing about this is that you always know that these are 16 bytes. Okay, it's nicely organized. So we see the header. We see some things that LD decided to generate for us. BSS start, eData, SIM tab, STR tab, STR stub, and that's what we have. Even though there was no start, even though there was nothing. So we go ahead, we practice our redoffs skills. I really don't know why it doesn't put it like into by default. Okay, so we see that indeed we have like section headers generated. Here we see entry point address is 0. And what would happen if I try to run this file? What do you think?
Crash.
Yeah, so it will segfault from several reasons actually. But what we'll try to do is execute entry point address 0. However, and this is actually advancing something that, preceding something that I will explain later. I mean, what does it even mean? What is 0? 0 where? I mean, we know at least in user space that we have virtual address spaces. Where is 0? We know for sure it's not physical address 0. And we know for sure, hopefully, that we didn't put anything in page 0, in address 0. I mean, the kernel will not permit it anyway because of all kind of like antique exploitation and stuff like that. But it doesn't work. It won't work. So there is something that is missing. Sorry, like the mapping here that we saw before when we had, for example, our LD on the file that had main. Okay, so this is not enough, but it's something that exists. It works, and I will not even bother to run it. Okay. Now, here's some example on how things look like in Hex Dump, and this, which is exactly what I did now. Okay. Now, if I want to go ahead and create a file, okay, and now we'll start using the 32-bit x86 architecture. We'll give it the parameter -m machine elf i386. Then what I can do if I have an object file that like I compiled or assembled, I can use LD, give it, okay, and then -o gives me like the other result. And then I can run it. That is, I can, instead of doing GCC and having a.out or whatever, I'm going to first compile it. This is gcc-c like I did with the object file. And then I can go and run LD with a linker script on it. If I have an assembly, an assembler I can go and do with the --32. This is Intel, but the concepts are the same for 64-bit Intel, of course, but without this --32. And for ARM and for MIPS and for PowerPC and for everything. So let's have a very simple source file that doesn't do much, okay? Who wants to tell me? Somebody complained about AT&T syntax before, so go ahead and tell me what it does here, okay? What this simple file does to test your knowledge of like trivial assembly. Anybody want to tell me? Okay, so I will tell myself. Ah, somebody told me. Yeah, exactly. So exit with exit code 42. Why 42? Because it's the answer for everything, right? All right, good. So That's exactly what's going to happen here. So I'll tell a little bit more about what this does. We declare in my assembly file a section, so the linker will know it. We said it's allocatable and executable. I mentioned what it before. We said that some guy, my starting point, his name is, which is defined here by this label, is global, that is, it's external. Okay? And I put here NOP, which is going to be 0x90 because it's easily identifiable in the eye. At the end, I also put NOP. NOP will not do anything. In ARM, it's going to be, for example, move R0 to R0. Okay, something that is, all right. And x86 has a lot of instructions, so it has an instruction also for no instruction. And what we do here, and this is AT&T syntax. So all those who learned like in the army in Israel or before, we learn assembly and we disassemble, they usually are puzzled by the syntax because they're used to something called the Intel syntax. So in the Intel syntax, we'll not have the type like the L, okay? I'm writing here just because to not switch tabs. And we'll have something like move, EAX, right, and 1. This is what's going to be without dollar. Dollar is immediate in ARM. In ARM, it's this. In AT&T syntax, in GNU syntax, and we don't need like the register. Okay. So we move this. We move 42 to BX, right? And what this does is, this is the opcode for interrupt 0x80. So I'm not going to say too much what it does, but what it's going to do is just somebody else, in this case the kernel, will execute some service for us, and the service will look at this one. In this particular case, it's a system call that its number is 1, that I can see in user include whatever, that it's exit. And 42 will be the parameter to it, okay? So I will later show you how to test correctness for this. How do you test correctness for this? You build it and echo $? Okay? And if you do that, then everything is good and everybody's happy. So let's go and try to like build it. If I just go ahead and build GCC of this guy, it will say, hey, there is undefined reference to main, which is exactly what I would have if I build a C code without having main in it. Okay? So this is the default of GCC and LD. They look for it, and in particular, they look for the C runtime. Okay? That is the one that calls main. So these are the errors. Now, let's go ahead and go look at a trivial solution. So a trivial solution, the first trivial solution, is to add a function and call it main, link with libc as regular, and everybody will be happy. Okay? So this is a trivial solution. What's the problem with it? So there are a lot of problems with it. We just did a program that doesn't do anything. It just exits. Why do I need libc for it? It's crazy. Okay? So there are other problems, but we want to be short in time. So the other solution is to take control to our hands. Okay? So let's first see the problem with the first solution. All right? So here it goes. So I called the file using from assembly.s, and I said that we have main. In this particular main, I didn't do anything. I can skip the knob completely. Okay? And I said, all right, this is my starting point. You would usually have section.text over here, not this one, just so you know. Okay? So the result of this friend would be a.out. That would do something. Okay? Now, let's go ahead and see like what happened here. This is not the code that I wanted. This is not my starting point. Otherwise, you would see 42. So what happened here? These were the values that were in the register appropriate to it. I could debug it. I could see everything, and everything would be just fine. Okay? So let's have a quick look. Oops, on the executable. And see the sections. We see all the libc bloat. It's crazy. Okay? We see relocations. We see this. We see that. And we see that the entry point, for those who ask about like the ELF, is 3b0, okay? That is going to be actually relocated according to all kind of rules, okay? That we're not going to talk about exactly now. And some of the things that we see is that there is like a linker here that uses it, and it will load libc. And if we actually go ahead and look like with a debugger on it and start on like the start symbol, okay, then we'll see that this is the entry point that we have. And I'm telling you it's from libc, okay? We'll have libc start main and so on and so forth. And I can go ahead and break at main or do start like we like. And then I can see that this is where I am. We have the knobs and like the backtrace. Okay, there is no really backtrace here because there were like all kind of like trampolines and things like that. And like the frame was not like so-called properly set, okay? But if I look like at the registers, and this is also like a practice on like how to see all these kind of things, then I can see that this is like EAX and this is like EBX, and these are like the things that like there is no like exit call. So they're going to be whatever is going to happen, and that's it. All right. So this is the very simple case, and we don't like it, okay? Because yeah, we had a shared library, which is good. Things could be much worse. We could actually have like a static library here into a.out, and this absolutely nothing would not happen. But the other thing that didn't happen, okay, this example, we didn't even look at the code that we built because we just added main to make it happy. So this next thing we can do is say, okay, we can do something else, and will not, or either not use GCC or use GCC and pass it links to the linker. So the next step is going to be, okay, we assemble it, and then we take the object file and output it, okay? Now, this is not good enough, all right? Because, all right, what are the default parameters of the linker? So we can go and start controlling the parameters. So one of the parameters that we'll have, like say, okay, we want to have 32-bit parameters. And if I do not have the underscore start one, pay attention what I did. I have like LD. I did not use GCC. And I said, this is your input. And this is your output. So this is all that it's going to take. And it says, hey, I can't find the symbol start. So I'm making one up. Why not? And this is going to be like the symbol of it. Okay? So if I look at the file, this is like NM, like the mapping. I will see that these are the symbols that have been generated for me. And if I run the file, I'll see that it's 42. By the way, it's okay that I'm going over slides. I did it just because of the request that I had. You know, I prefer to show it in command line and to explain everything. All right, those who know me already know that. All right, so this address, no comment, I assume everything is good. So this address was actually given to me like automatically. Why? Because LD decided to do so. So I can start and control also this. So I can go and say, hey, like maybe I want the entry point to not be this one, but to be something else. So I can go ahead and provide it the -e address and so on, okay? And if I want to see what got in like the ELF, then I will see this particular one, okay? So if I went and instead of this, I give it like a 1337, then I will see something a little bit else, okay? So let's see what we have here. I don't even know what we have here, but let's have a look. The assembly file itself, it looks the same, okay, without main. And if I go ahead and look at the default one, I will see that it has this entry point and these symbols, and I find custom, which I defined in assembly files, receiving its section, and it's receiving an address. Check it out, 804.8054. Okay, it's receiving it, and it's great. I have like an undefined symbol that was generated for me that is called start, and everybody's happy more or less, because something like start is going to be defined like elsewhere perhaps, and like that's it. All right. Now let's have another look at this out E. Oops. Then I can see here that here I have an entry point address of 1337. So the rest was automatically generated. Okay. And if I actually want to go ahead and run this, then I need to see if somebody defines 1337. Now, what will be this address? It will be the address upon loading. It will be a virtual address. When I talk about user space, okay, when I have virtual things, like sometimes the entry point will not even be relevant if you just want to have an elf that another bootloader knows and jumps like to a very known location. It's not even relevant, the entry point. We'll see later when you boot the kernel. So we have this, and if we want it to make sense and like want it to match our custom section here, then LD did some things for us. It actually generated an address for us somewhere, which is nice. But this is just on the disk. What do we need to actually make it mappable into memory? We need to define a mapping. And this is what you know as like the segment, the runtime segment. Okay. So the idea is to have something called, also defined by the health, a program header that will have like a virtual address and all kind of parameters. Okay. And what we have here is like a mapping of like, hey, this is something that will be loaded into memory. How, or what is like the matching that the linker will put here by this offset in the file. Okay. So if I load it correctly and I jump like to the right address, I will be able to make things work. This is an oversimplification, but a true one. Okay. So if I went and did this, this is exactly what I showed you. All right. So these are the program headers. The section header, pay attention. And I actually showed it on the Hex Dump, what I'm showing now. Pay attention to the colors. I have here several sections. I never asked for sim tab, str tab, and the section header tabs. I never asked for them, but they exist. Now, the idea is this. Look at the address. We have here like the pink, the purple, the blue, and custom, which is where I put my code. Okay. And if I look at the file with Hex dumps, and I will get back to this again, I see that like in out E, under a particular offset that is set by the section, see, 64, I have this binary data. Under D4 and 1115, I have these strings. Now, every time I have strings in those sections that are str tab or section header string tab, okay, then each string starts with a null here. Okay, that's how it works. So we start the section like with a null, and then we have like we're also separated by a null. So it's true for all of these sections. Debugging information is something a little bit different. Debugging, it's not debugging information, it's simple table. Okay, debugging information has extended. So we can see that the debugging information as the simple table, sorry, it has a size of 70 here, okay, 70 hex. And if we look at the symbol table, and if we look like how health is actually comprised, then for the 32-bit, we have the following structure. We have like name, address, size, info, other, and so on and so forth. So if you look closely, you will see here all kind of addresses. And I actually put it like in some tables to show how these things align like in memory. Okay, so I'm not going to talk about it too much. It's like in an ELF structure, but we have actually very good descriptions of this. So what are these addresses here? And what are like these names? So a name is going to be an offset in the string table. Okay. So this is why you see like these strings like on the ELF and see like what's going on. And the address is where the address itself is going to be. Now what happens when I go and strip an ELF? What's going to happen is this is the exact same thing, okay? This is like the Xdump, but this is after I strip and Xdump it. Then I get rid of what I just showed, like the simple table, okay? And the offsets here modify. So after this, I see other things. Like I see that I still have some strings here. And I see sh, str tab, and dot custom. So after the stripping, I have two sections, okay? Custom and section header str tab that is required to even describe like this table that we're seeing. Now, why am I mentioning it? Because many times you want to discard things using linker scripts. However, LD will not let you do it for some of the sections. Script will let you do it. Opcode will let you do it. Okay? All right. Any questions so far? Are we good? Are we interested? Actually, if we're interested, like it's also a good question because I can go billions times faster. Is anybody?
I think it's interesting. Yeah.
Good. Is anybody still listening?
Yeah, it's interesting.
Yeah, good.
Yeah.
All right, Israeli people, you're here?
Yeah.
Okay. All right.
לגמרי כאן.
All right, so jump. What's the problem? Okay, so I said all these kind of things because this is like, for example, like complete stripping of symbols is not something that you can necessarily do from like the linker script. You can specify some things and other things you can't. Now, let's talk a little bit about the format, about writing our own scripts. So far we showed like linker scripts that like were done automatically by LD, and now we'll do some other things. Very important thing prior to that. If you remember, and if not, maybe look at the recording and then look. This program header was not output in the default linker script when it did LD -- verbose. So people, people kill themselves over it from the depression, or like from the frustration that, hey, I want to learn like how to do it right. I want to do exactly what LD does, but hey, I'm missing a very important piece here. So you can't do everything, okay? All right. So how does linker script look? There are also many other things like memory and like discard, but I'm not going to talk about them. I'm just going to talk about the basics. These are the formats for comments. Entry is a name of a symbol, defines it. Section is section descriptions, and then you actually specify how the section of the ELF look like. P header is program table, okay, program header description. Dot always refers to the current address. Everything that doesn't end with right, left, with a closing curl must end with semicolon. There is no concept of white space. I mean, okay, one white space means something, but millions don't mean. And sometimes white space, the one white space is very important, okay? So you need to be careful, like not to do x equals and space y, or like the other way around, it might not work. Output format will tell the container architecture, as I mentioned. Arc is for a specific machine, and you can include other files. Why am I saying this? Because you can just, like, for example, go and have like a linker script that just include a file and put it like in a section. Okay? So there are a lot of things. And it's important to understand what you want to do. It's important to know like the address. It's important to know if somebody loads you what they expect, and so on and so forth. For example, like in Linux, let's say that you want to make like a memory mapping, then you will see that unless you specify in the linker param what is your required mapping, then everything will start not in a 10,000, but it will start in 200,000. Why? Because, and then there are lightweight requirements, and you may do some things and not understand what's going on. So it's important to understand some of the things. Okay. Now, so we got here. We want to customize our own things. I mentioned before that -T is going to take care of having your own linker script. So if I just do it on an empty file, it will say, hey, no input file. Why? Because LD doesn't work only on a linker script. It actually expects also another file. So what I'm going to show you now is actually how to create like an elf script without any code. Okay. So we need to provide it at least another empty file. Now, this is just like before with the LD. If the file is empty, it will not work. If you just have a comment, then it will work. So if I just have this LD-T and do it without the default linker of behavior of LD, of Linux, of whatever, then I will have an output file that I can try and run, but then it will say, hey, it's like a corrupted program. Why? Because it's not made in the right way. So if I went and show, then I see that these are created by default by LD because LD was configured to do it. And I see a symbol table that has an empty entry here with all zeros. Okay, and I see that this is where the program headers start. And I see that the section headers start here, these guys, and I see the entry point is 0. Perfectly legit, working. Okay, if I compare it to the default of a linker script, then I see things that are a little bit different. Okay, so this is how it looks. All right, this is my script, and this is the default linker script, unlike the empty file. Fair enough? Here we see additional things like PSS start and so on. And this is the difference between the files. It's not critical. You can do it yourself. Now, let's start writing a script. So the first thing we'd want to do is go ahead and say what is the output file that I want to be. I can specify it, or I can give the -O parameter. So if I have output, my output here, then the name of the file is going to be my output. Okay. Output format ELF32 means that I'm going to have an ELF32 container for Intel 32 bits. And here I say entry my starting point. What does this mean? It means that I will be expecting some file that is called my starting point. Sorry, some address that will be my starting point needs to be an address. What is an address? And this is a very important observation. If I have here foo equals, I'll go to terminal soon, I think. If I have here foo equals 0x foos, it means that foo will be a symbol that its address is 0x f000. Same for bar. It's not their value. You can define a value in a linker script, but this is not their value. Okay? So if I go ahead and take this and build it, I will see that I have an ELF file. And it will look like this. I'm going to go a little bit quicker. I just took the, I decided to like show all the different sections here. And there are a lot of things that we don't have. We can do versioning, especially useful like for libraries. And we don't have program headers, so this will not be loadable. No dynamic sections, but there will not be dynamic sections in these tutorials anyway, and so on. So what did we have like in the section headers? Okay, so we'll usually have a null section header that will be automatically generated for us. Okay, and if we have a look, and I remind you, we had like this foo and bar 7. This is my foo and bar addresses. They were not defined in any section, okay, but they were defined somewhere. Where are they defined? In the symbol table. Okay, so what is their value? Foo is this and bar is this, and if I do nm on the file, I will see the same thing. Okay, so I'm not going to go over the Hex Dump because we already know I showed things several times and for several different perspectives. We already know more or less what's going on. And if we're not, you need to jump on, all right? And on the mic. So what we create here, we have these three guys that were automatically generated for us. We did not define any section anywhere. So that's all we have, what was defined for us. Good. So that's what we have. And we can see that the symbol table is at offset 34. Where do you know it? Because the section table tells us this, all right? And every entry there takes 16 bytes, and we see that there are 1, 2, 3, 4 bytes, and this is why the size of it is 40, okay? And this is why the next section header is 40. It's not, it's X40. It's 40 after it, okay? And here we were supposed to have something, but I already explained it. Like, I don't know why this overridden the other one. All right? Now, my starting point is undefined. UND is undefined because I just said it exists. I said it's the entry. I didn't do anything with it. Now, what happens if I want to create sections? So section is being done like this. Section, I'm section, dot, I'm section. Anybody wants to guess? Okay, I already I already gave the answer, so never mind. What's going to happen if I just have sections and have no data in it? Then they're going to be discarded by LD. Okay, there is a keep that helps me do all kinds of things. Okay, and I can go ahead and inside the sections specify a symbol or like an address. Okay, I can also go ahead and say, hey, this section will start at 0x 200,000, or this section will start, dot is the current address, at 0x1000. So if this happens, it means that if I have all kind of definitions here, like I defined foo and bar before, remember? Like I defined foo and bar, they were not in a section. So it's like the next available address. If I like wanted like to assign something, to assign like dot to it. But if I have the sections, and if I have like address description, then it means that the definition of whatever I want to define is going to be under it's going to be like on this address, okay? But since I did not define like any data, I just specify like addresses, the sections are likely to be discarded as well, okay? So what would be the continuation of it? Look at this. This is like this guy, 2,000. Check it out, 200,000. I am var equals 5. And it's an address, as I told you before. I'm not defining here the byte 5. So the address is going to be here in the orange, 200,005. And beef, if I add to it 1000x, it's going to be sif. Okay? So that's what's going to happen. So I can actually go ahead and use the keep word that I will explain in a bit in order to decide, like, okay, let's say that I have all kinds of files that are linked with the linker that takes this linker script as its instructions. I can go and keep like symbols from other places that would otherwise maybe be discarded because they're not used, for example. But there is a way, regardless of the things from other sections, from other places, and so on and so forth. The syntax here says there are regular expressions you can say of which files, for example, okay? But this says from every file that was given to me, the linker as an input parameter. If you see there is a section that is called IAM section, keep it, okay? That's like what it says. And this is a section that is called .IAM sections. They're not the same, okay? Deliberate. Now, here is the thing. Let's say I don't want to be dependent. I can define data here. So look what I do here. I defined long 1, 2, 3, 4. I defined a byte that is the value is 52. and here a byte that its value is 6F, and here a byte that its value is 6C, and it's a byte that its value is 4D. Anybody want to guess what's that? So if I go and give this linker script, okay, that again will operate on an empty input file, but I will give a linker script, ld-t linker script, and the empty file. That's what I get. No source code, no nothing. So what I get now is .im section. It will exist because I defined here things. And what did I define? So here it is. I can see here a string somewhere. I can see Ron M. That's interesting. Why is it here? So Ron M, here we see that we have like 1, 2, 3, 4, 0, 0. And then we see 5, 2. This is RONM. So we have this long that was 1, 2, 3, 4. Okay, this guy. And they are padding zeros, right? Because it's a long. So what we have here is like these ones. And because we are little endian, then we write, when it's like long or an integer, we write on the so-called opposite direction. Okay, we like look at the memory like this. Okay, so we added thing. All right, great. So if we added code, if we managed to add code, if we managed to add data, why will I not be able to add code into it? Okay, so look what is going on here, or like what happened here. So here we have this section, and actually this is a later example, to be honest. But we have like this Ron M, okay? And I will show you the code that also had the NOP, because it's not like on the slides. And if we define some things, then we can also have these nice fellows here. Now let's get back to the sources here, okay? This is the example that I was interested in. So here, look what I have here. I have this section, and I defined this guy, and I defined Ron M. And what I also define here is another section called NOP that defines AAAAA, and another section that has BBBBB. Now, if I look at the memory, I also see 90, 90, 90, 90, 90, 90, 90, and BBBB, and so on. Now, why? What's going on here? The thing is that if I go ahead and depending on how I define the sections and how I define the alignment instructions, then I can have all kind of gaps, and I can decide what code like to fill the gaps with. All right. So this is like another section. Okay. So I'm going to now go ahead, and after I showed you a little bit how to generate some things, okay, generate some information over here, and write all kind of bytes. If I can write this byte, I can byte. If I can write Ron, I can write a code that actually works. And like 90, this soap, it's something I can feel it, and so on and so forth. I can go ahead, and if I manage to do it, I can actually put real code in it. Okay. So the idea is like this. If I want to program and run only with the link script, then I need to know how to create data, and this we already know. If I manage to write Ron M inside of a memory section, when I just add a linker script, and I can write the bytes that will make code for it. Okay. So if I want to run some code, I will create the data. I will set the entry point for it. I could put fill patterns or maybe not. In my examples for the longer time, I also show all kind of how to like memory tricks and things like that. We'll not do it now. Okay. And just to keep it short, but if somebody is interested, I can do like another session on that. And what we need to do is to manage to load it into memory and to have the access codes, the access mode. If like If I have MMU, if I have memory protection unit, then they are of course not the same thing, okay? Like in the Cortex-M, if I have like MPU, then I want to make sure that I'm loading things to the memory. It will go in pages, okay, if there's like protection, and that these pages have like the right access, okay? So the strategy for that will be to know what we want to run where and to mark the sections. For example, this AX, allocatable and executable. So have a look at this one. Here we have some instructions, okay? And I put here something that looks like this. I just emphasize the important things. It's like the same linker script and emphasizes important things. This is why I also always like to do terminal. So like the people will not like lose track, but it takes more time and switching between this and slide and so on and so forth. So it's like calibrating of like this virtual meetup when we're like on class, it's easier to see what's going on and if people are following. So here goes, like I put a section and I just put here bytes. Instead of writing my name, not that I don't like my name, I have a great name, I just put here bytes. Now, you can actually recognize that we have a move instruction here. Okay, only if you know this, that we have move, another move, and the CD80, it's easy because I said before that CD is int and 80 is 80. And we know that 90 is a no-op, okay? So this is IAM section. This is what I have here. If I go and link it, this linker script, and I selected this starting point, you know, just for fun. I can use it, I cannot use it, and I use like the entry for it. Then look what's happening. Can you see this? If I disassemble IAM section, that goes to address 200,000. Okay, and the reason for it is because dot is like the current address equals 200,000. If there was a question, please tell me in the microphone. I heard some notification, but I don't want to interrupt, okay? I will not see your chats. So
I said it's definitely easier to follow on terminal.
Excuse me?
I said it's definitely easier to follow on terminal.
Yeah, I know.
Yeah.
Yeah, so we need like more time. Yeah. I'll go back to the terminal. I'll show again, okay?
All right.
So we're almost done. Why almost? Because look what's going on here. Like we have like this 200,000, okay, that I defined. And if I disassemble, I see that the bytes do exactly what they did in the assembly file that I wrote. So this is great. And here we have this IAM section that its address, its section address, well, Object Dump agrees with what I say, all right? Pay attention, I did this -D, capital D means disassemble also non-text segments, okay? And here I see that it is allocatable and writable, which is okay, it's good, but, and if I look at the program header, I see this, I see that we have load, and I will go and talk about it soon, what this means. And we have these virtual physical addresses that are zeros. And we also have like a flag that is RW, I don't see execute here. And the mapping that we have between this section and this header is here. I have like, hey, IAM section is here. So this section will go here, and this is not executable, and it goes to virtual address 0, and you don't care about physical addresses in this particular case, okay? So we're not done. We're not there yet, okay? We're still missing, okay? So let's take a little stop and just understand what is the problem that we have. The problem that we have here, you know what it is? We didn't say how to load things to memory. So I actually don't remember which of the part it was. So let me just check. I think it's step 3 or step 4. This is the playground linker script. This is the previous one. This is, let's see, step 4. This is the one that has the name in it. Step 5. Okay. All right. So basically, I'm not showing this yet. I'm just showing you that there are several ways like to do things. The idea is that we need to define program headers, okay? And somehow automatically do like the mapping. I'm not doing it now, okay? I'll first go the embedded way, the embedded part, which I hope and believe is this. I think it's going to. So here goes. Basically, the first solution that every one of you, whoever wrote like a linker script, definitely defined it like with sections of like ROM and RAM or like their board, is to go ahead and say, hey, I am going to define a memory area that will start at a particular address. And this is going to be like its length. 14 is a ridiculous number, okay? And then on the section description, I will have this nice fellow here. Code is the name of it. I could call it whatever I want, okay? But I'm section, after the braces, I will redirect it to code. Okay, so hopefully this will cause us the mapping. But what about these guys? So the mapping is going to take care of this, okay, of the addresses. But what about the execution thing? So the memory region will also specify that it is executable. Okay, so this is the idea. So if I went ahead and used it, then the result will be that we have a virtual address and we have also a physical address in the same case here, and we have those flags. Now let's do it together, okay? So let's show it from the terminal.
Would it be possible to also link the slides?
Excuse me?
Would it be possible to link the slides?
Yeah, I think so, at least part of them. I'll need to reorganize it. I will need to reorganize it and somebody will need to remind me, okay?
Sure. Thanks a lot.
Sure. This is why I like the, the going slow thing. So that you can do when I do, and like you do things like in a meetup, and then if things don't work, then okay, maybe later you go back to it, or like you talk to me after, stuff like that. Okay. So here it goes, and I definitely gave like over like 50 talks in conferences in my life, probably over 100, definitely over 100, I think. But I gave like thousands of, hours of courses and all these kind of things. In the talks themselves, I don't like reading from slides. I mean, I just don't like it. But actually, I'm reading from what I pasted like now, because some people like asked. So sometimes it makes things a little bit clearer, okay? So here goes. So when I talk, whoops, that's not what I had in mind. So my linker script looks like this. I defined code and origin here, okay? And I redirected it to code. Just so you know, I can use equals also after. It's a syntax. I'm not going into syntax. To have a filler of 11111. And I can also use the fill keyword in order to have that, okay? My starting point is 200,000, and origin is a keyword that says, hey, this goes to 200,000. And so here we have the mapping, and everybody is going to hopefully be happy once I do that. Now, if I do that, Here we have a segmentation fault. Actually, I think this is not the file. So I'll go to LD-T playground with memory and empty file. Okay. Sorry, I was running something else before. So here we see 42. Okay. So what we have here, like if I go ahead and do like read elf-a on this guy, I see what I showed like in the slides. So we have load, we have read write segment. Okay. We have this nice fellow here. We have an entry address, entry point. Where is it? That is 200,000. I can actually make it like smaller, but then I will need to add another linker parameter, okay? And if I want to prove that I'm not bluffing, then I can go ahead and just do like this, like debugger, and debug my output, break, star is very important here. Run, disassemble will not tell me anything because like there is no frame. But what I can do is X, let's say 40 instruction, $PC. So I want to disassemble it. So I look at the instructions here. So 40i, and these are my instructions. So here we have all kinds of things, but we'll never get to there because this is a system call that calls exit, okay? So if I go and do SI, and SI, and SI, and let's just for fun do like set disassembly next line, disassemble, sorry, next line on. Won't help because why? There is no next line because this is a system call. Boom, terminated. All right. So this is how we actually did it with memory, and one can actually go ahead and take care of, without specifying memory, they can go ahead and define the program headers, okay? So having said so, let's go ahead and after we are convinced that we are able to create a working program without any assembly source file, any C source file, just with the linker script, then we understand a little bit better how things work, okay? And some motivation. Does it make any sense?
Yep.
I just want to see, I consider him a friend. I just want to see if the one who complained about the terminal is here.
That's me.
No, who complained. You didn't complain.
That's not me. Yeah.
The one who complained about the previous time. Yeah. You praised the terminal. No, I'm joking. All right, friends. So here goes. So what another part now? Like what's happening if like we want to use like a custom script, but we want to actually link an object, like how stuff really works, okay? So what we'll do is this. This is the program, you know it, that we're going to work on, okay? It's the same one from the beginning. And we will build it, like we will assemble it. We'll have an object file. Okay. And then if we look at the result of it, we'll see that like the object file, it indeed has like the sections and whatever we expect. All right. So we have the custom that we defined here. Okay. We do have .text here. And the reason is because .text, .bss, .data, not because we decided to have them, okay? But the assembler decided to put them for us. Now, you saw on other examples that we shown that these were discarded. Now, why? You should already understand by now that if I don't have anything in a section, boom, it goes away. All right? So let's go ahead now and take this fellow that is in my custom section. Usually you would have, but not in the Linux kernel. Oh no. Usually you would have like that text segment that like is the executable one, and this is where you'll find like your functions and so on and so forth. But here deliberately, I do it another way. Okay? So here's the thing. Maybe, by the way, I mean, if somebody's interested, like maybe I can just like put the source code like on GitHub or whatever. Let me know like if you want that. So here's the thing.
At least I would like that.
Okay, remind me and I'll do it. So here it is. So pay attention. Like the linker script that we're going to add, I call it my. Will look like this. It will have an output. My output, same name. Output format. Same output format. Output arc, same arc. And the entry is starting point. Okay. Now I put it shorter for the slides because it's not important. When I open like the file, you see some other thing perhaps. But basically, we can have or discard some addresses that I define. If I define them, great. Then we'll have like, if I look like at the object, they will be on apps because they are not inside the section. Okay. But here comes the mapping that I mentioned several times. Now, to make a very long story short, we care only about the custom section because it was defined in the file that we want to link. We created an object out of it, okay? Because we assembled. And we want to take this section and from an object and include it. Now the terminology is going to be like input and output, but I'm not going to talk about terminology. I'm going to talk to you like, you know, in a plain human form. This line does the following thing. It says, hey, the output section called custom, output section means goes into the end result, will be comprised of every file that you give me. For example, if we later link ufa.o, that whatever is in there, and it has the section, as you already know. And what's inside this file or inside these files? Every section that is called custom. So if this is not empty, and it's not empty because we wrote the code, then it will be set here. Now, before we saw the following thing. Before, sorry for that's easier. Before we had this, we had like section, right? Whatever. Needs to be sections. And here we had some stuff, right? We defined data, and we redirected it to my awesome memory, right? That's what we had like before. But now I'm doing something else, and you could and you should look at where is the output section? At the manual, which is in sourceware.org binutils docs LD. Okay. And there you can learn that if I have this nice column here, then this is the name of a program header. Okay. Now, to understand what program headers are and what is like interesting and so on and so forth, you can take readelf on like pretty much any file and you will see them. Or you can look at the include files of the ELF structures on Linux, or you can look at the ELF specific standard, or you can do all kinds of other things. But to make this very focused, this line says this. I define a single header, program header. This is what will be parsed at runtime. When you talk about the Linux kernel, you will see how it's happening. So what I say here, PT, load, means load this into memory. File header means that it's going to have the elf header in memory. And P headers is going to include all the headers in memory here. Okay? Now there are rules that when you have what you can specify before and after what, that I'm not getting into too much. Okay? But what we do here is assign this custom guy to here. Okay? And before we also like specify an address. So this is the mapping. I remind you like from before, we had like this red and green. This is like going to be like the mapping between a section and a place in memory. But before we resolved with a memory. So the result of something like that would be if I link it with my linker script ld-t ufa.o, and I can go ahead and look like at the output. So my output will go and have the symbols. Like my starting point now has this one, you see, 20054. We have here the section that starts exactly here. And we have like the virtual address that is aligned right here as well. We have the entry point here as well. Okay? So what we can also see is that unused sections like .text were removed. Okay? And I will show now like the result and like what we are interested in. So a little bit before it, let's go to step 6. So this is our source file that had this label, okay? Before linking, when we just assemble it, we got this fellow. And now I will disassemble it, because when I go over like the kernel, I will use it a lot. Yes, I can use other disassemblers, but no need to. When I disassemble it, this is what I have. So-called address. This is the object, 0. This needs to be relocated. This needs to be loaded somewhere in memory. This needs to be somewhere in memory. Okay? If I disassemble like everything in it also as data, I will get the exact same thing. So my starting point was not defined at this particular place. Okay? Just so you know, you can use nm on it, or opcode-t, which is the same. J would help. Okay? And look what we have here. We have symbol table with these guys, text, data, BSS. This is AS fault, but it's going to be discarded. Okay? So it shows us that there are sections. You see like this L here. And here we have a global one. Okay? So we can also go ahead and see this object-a in UFA. There are several ways to see everything. And we can see what was created for us. So because of the A and X we have this property here. Okay, like read-only code, just like text. Data, for example, has only this data. And BSS, you can see that it's only like allocatable. Okay, so we learn like how some of these things work, and they are all discarded. Of course, if we do readelf over it, then we'll see the same information. All right, section headers and so on. This was our object file that I remind you we got from using from assembly. Okay. Now, let's look at the linker script. So the linker script add the following thing. Now, in this particular case, I also decided to add another header with the headers in its own section, okay, with the pt ph there. This is its type, okay. If I wanted, I could go ahead and specify an interpreter. So if I just have this section but don't specify anything for it, then it will say, okay, interpreter, and like, hey, I can't read it, or like, what do you want from me? But I don't care because I don't have like dynamic sections, for example, okay? I don't have a data section that I want to load. I don't care about it. And these things, when you see text that I just names that I give, they are not really important. So I can just give custom as I did. So in this case, I defined some things. I defined some section in another section, but they don't have anything. This is a definition of an address that I can discard of the section. I don't care about it. And I don't import anything from another file here. What I do is this guy. And what I say here is, hey, I want custom whatever is in here in this section and is mapped to this name, and I could call it any name that I want. I want it to start on address 200,054. And I want it to come from all the input files in the custom section. So here I want to do that, and that's like how it's going to be done. Some variable is another variable, and that's it. And here I could discard sections that were included from other files or that I find here, but I will not be able to discard like the sim tab or like the sections. Okay? So at the end of it, when I link, I have this fine gentleman here. Let's do opjump-t on my output, which has the new address, okay? So everything is okay, and you already saw the output of readelf over here. Any questions? Okay. So this is like how you are going to do linking, essentially. And this should go in another section, I think. I mean, I think we should separate like the talks perhaps. But are there any questions? Do we want to start the kernel session now or leave it for tomorrow? It will be very long. There are two sessions there. There is debugging and there is like linking.
I think tomorrow is good.
Okay, I will talk a little.
Yep, same.
Excuse me?
Same. I think tomorrow will be good.
Okay, and for starting now is also okay?
Yeah, sure.
All right, so give me 1 second and like we'll think, okay?